Hey everyone, and welcome to section 10.3 about evaluating and graphing logarithmic functions. So let's take a look at some of the kinds of equations that we've solved in the past. So how is it you would solve each of these equations? Well, so in this first equation, you're adding. So to solve, you would subtract. In the second equation, you would add. In the third equation, since you're multiplying, you would have to divide. In the fourth equation, since you have a square, you have to take the square root. And for a radical function, square root of x equals 13, you would square both sides. So in solving equations, the basic premise is doing the opposite, essentially, of whatever operations have already been done to the variable. When we talked about exponential functions in the last video, the equations that we solved didn't exactly use this idea of doing the opposite operation. So for example, if we had something like this, 3 to the x is equal to 7, in the last video we tried to basically write the right-hand side as a power of whatever the base is. It's easy for some values, but for this one, it wouldn't be so easy, right? I don't know what exponent of 3 gives me 7. So it's really difficult. And in fact, it's so difficult that we have to introduce a new function to do it. And that is the logarithm. So the base A logarithm, written log base A of x, is defined to be the inverse function of the base A exponential. So in other words, if I tell you that y is equal to the log base A, that is saying the same thing as a to the y is equal to x. So we can take these equations here and translate them into the other form. So log base 2 of 8 is saying 2 to the third power gives me 8. Whereas this guy, the second equation, is saying that the log base 4 of 64 is equal to 3. So when you feed a number into a logarithm, you are getting the exponent as an output, essentially. And there's two kinds of special logarithms. We're not going to dwell on too much, but we have the base 10 log, which is called the common logarithm, and when we write just log x without a base, that's what we're assuming we're talking about. We also have the log base e of x, which is called the natural logarithm, and that's usually written as ln x. So the base 10 logarithm, the common log, is useful because we use a base 10 number system. But rather confusingly, there are also some settings in which the log x refers not to the common logarithm, but the natural logarithm. Don't worry about that too much. It's just, if you see these guys, you're talking about the common and natural logarithm, respectively. Right, so maybe let's look at evaluating a logarithm, see how that goes. So f of 1 would be base 2 logarithm of 1, whatever that is. This is saying that 2 to that power is equal to 1. Well, we know that when we raise things to the 0 power, we get 1. So that means that f of 1 must be 0. For part B, we're taking the base 2 logarithm of 2. So 2 to what power is equal to 2? Well, we know that one. It's 1. We have the log base 2 of 8, saying 2 to what power equals 8. We know, of course, that that's 3. All right, f of 0. So we'd be saying log base 2 of 0 would be saying 2 to the what power gives me 0. And if you recall from our discussion on exponential functions in the last section, well, we know that the exponential is never 0 unless it's been moved up or down. So actually, this is undefined. Okay, well, what about a fraction? So 2 to what power gives me 1/2? Well, I know 1/2 is the reciprocal of 2, and the reciprocal of 2 is 2 to the negative 1. So in other words, this is negative 1. And lastly, the base 2 logarithm of negative 3 means I'm taking 2, and I'm trying to figure out what exponent do I raise it to get negative 3. Of course, since the exponential never crosses the x-axis, this never happens, so this is undefined as well. So the logarithm function is positive so long as x is greater than 1, and negative if x is between 0 and 1, but it's not defined for 0 or a negative number. In particular, log base a of b has a vertical asymptote whenever b is equal to 0. So whenever the inside of the logarithm is equal to 0, right? So this f of x has an asymptote at x equals 0. You could also have like log base 2 of x plus 5. And if we solve x plus 5 equals 0, we get x equals negative 5. So that would be a vertical asymptote for that. All right, and again, to reiterate that the logarithm is only negative if b is between 0 and 1. The logarithm is undefined whenever what is going into the logarithm is less than or equal to 0. So let's try our hand at graphing. So from the last video, I actually already know what 2 to the x looks like. And we actually evaluated log base 2 of x in the previous slide at a bunch of different points. So let's plot those. And then if we want some more points, we have to think about, well, all right, so I can plug powers of 2 into log of x and get a nice answer. So for example, 4, log base 2 of 4, since 4 is 2 squared, is going to give me 2. Log base 2 of 8 is going to give me 3. Log base 2 of 16 would give me then 4. And so there's the graph of our log base 2 of x. And what we should note here is that 2 to the x and log base 2 of x, their graphs look kind of similar, right? They're mirror images of each other, and that's not by coincidence. So an exponential and a logarithm that have the same base are going to be mirror images over this line. So let's summarize and compare a little bit the exponential and logarithm. We're going to get kind of more, we're going to get our hands dirty, so to speak, next section when we work with properties of logarithms, but the domain for these two functions is different, right? For a to the x, I can plug in any real number that I want and get a real number back. For the logarithm, I can't plug in anything less than or equal to 0. For the range, for a to the x, I'm not getting anything less than or equal to 0, but for the base A logarithm, I get negative infinity to infinity. So you see the domain and range are flipped from one function to the other, and this is a feature of functions that are inverse to each other. Now let's look at their shapes. So if a is greater than 1, we know that the exponential is increasing, and the logarithm does the exact same thing. It's a mirror image over that diagonal line. If a is between 0 and 1, we know that the exponential is decreasing, and the logarithm actually does the same thing. And as far as asymptotes go, the exponential functions have horizontal asymptotes at the x-axis, but the logarithms have vertical asymptote at the y-axis. So these are all very closely related. But anyway, that's kind of all I want to talk about. As far as the beginnings of logarithms, we're going to next look at simplifying some expressions using properties of logs, and that really is going to wrap it up for the class. So yeah, look forward to that.